Selective precipitation. The solubility rules and the KSP are useful in determining qualitatively if a reaction would produce a precipitate. A quantitative component is added to the above reactions and is discussed in the coming slides. In general, any salt made with a group 1 metal is soluble. Any salts containing the nitrate ion are soluble, and all salts containing ammonium ion are soluble. The majority of silver, lead 2+, and mercury cations are expected to be insoluble. In nature, metals are usually found as metal ores. The metal contained in these ores are in the form of insoluble salts. Making extraction even more difficult, the ores often contain several metal salts. Differences in the solubility of salts is used to selectively separate the metal ions as precipitates of simple metal salts. Consider a test tube that contains silver ions, lead 2+ ions, and copper 2+ ions in solution to be selectively separated from each other. A suitable reagent can be added to the test tube that will form a precipitate with one or more of the cations and leave the others in solution. The knowledge of the solubility rules, or KSP values, for various metal salts helps to accomplish this goal. Silver ion and lead 2+ ion readily form many insoluble salts. The copper 2+ ion doesn't form the insoluble salts as readily. We have KSP values for silver sulfide, lead 2 sulfide, copper 2 sulfide. They're all much less than 1, so not very soluble. Silver chloride and lead 2 chloride also have these very small KSP values. The value exists only if the salt is insoluble, and we don't have one for copper 2 chloride, meaning that it is a soluble salt. So we can precipitate out the silver and lead 2+ ions as chlorides since they have low KSP values, indicating that they are insoluble. Adding chloride should precipitate the silver and lead 2+ ions as the corresponding chlorides, but not the copper ions. So because copper is still soluble in a chloride containing solution, it will remain in the solution and the silver and the lead will precipitate out. Silver chloride and lead 2 chloride can be removed from the test tube. Now, once they're removed, how can we separate the silver chloride and the lead chloride from the solid precipitate? Notice the difference, significant difference between the KSP values for silver sulfide and lead sulfide. This is 10 to the minus 51 and 10 to the minus 28. That's a significant difference. With more control on the concentrations of sulfide ions added, we can selectively precipitate one of the salts before the other can be accomplished. So far, we have just considered dissolving solids in solutions. Let's consider the reverse process, or the formation of a solid or precipitation of a solid from a solution. When solutions are mixed, we can predict if a selective precipitation occurs or not. And we can explain it with the help of an equation similar to what we've used for KSP. That's known as the ion product, or Q. So the ion product Q, which is again similar to the reaction quotient, for solid calcium fluoride is given as follows, and it's written the same way. Q is equal to calcium 2+ concentration times fluoride ion concentration squared due to the stoichiometry. But the expression is written the same way, except that you see how we have this I here? We want to use the initial concentrations for each of those ions instead of the equilibrium concentrations, when we calculate Q. When a solution containing calcium ions is mixed with another solution containing fluoride ions, the precipitate may or may not form. The precipitation depends on the concentrations of these ions in the solution. Comparison of Q and KSP values help to predict the precipitation. If Q is greater than KSP, precipitation occurs to the point where the concentration of the ions are reduced to the point that they satisfy KSP. In other words, if Q is greater than KSP, then the products are dominant. And because we're greater than KSP, we have to shift that equilibrium back in order to reach equilibrium. If Q is less than KSP, then the opposite is true and no precipitation occurs. If Q is equal to KSP, the solution is saturated and there's no undissolved solid, so we won't see any precipitate. And at this point, we would say that the system is at equilibrium. Okay. If Q is greater than KSP, then a precipitate is formed as the number of cations and anions exceeds the solubility. So in this case, we will see a precipitate until Q is equal to KSP, at which point equilibrium is established. If Q is less than KSP, then no precipitate is formed. There are so few cations and anions that they all remain dissolved. And so more solid can dissolve until Q is equal to KSP. We would say that that's an unsaturated solution. Most of the problems in this section ask whether a precipitate will form after mixing certain solutions together, and then which one will precipitate out first. Here is a sample approach to solving these problems. Depending on what's given and the requested solution, not all the steps need to be taken. First, determine which of the precipitation reactions are actually possible and write the net ionic equations. Write the KSP expression for the selective precipitation based on the KSP values provided. 3, calculate the cation concentration of the slightly soluble compound. 4, calculate the anion concentration of the slightly soluble compound. 5, substitute the values into the reaction quotient expression. This is the same expression as KSP. 6, compare Q to KSP to determine whether a precipitate will form. 7, the cation requiring the smaller amount of the anion indicates which will precipitate first. Example 1, selective precipitation. To a solution containing 0.100 molar concentrations of silver and lead-2+ ions, a 0.200 molar K2S potassium sulfide solution is slowly added. A, what are the possible net ionic reactions in the solution? And B, which solid will precipitate first out of the solution, given the KSP of silver sulfide is 6.0 times 10 to the minus 51, and the KSP of lead-2 sulfide is 3.0 times 10 to the minus 28. All right, so these are both insoluble. They will form precipitates, given these very, very small KSP values, and also what we know from our solubility rules. So the possible net ionic reactions will be between this silver ion and the sulfide ion added from this potassium sulfide solution to form silver sulfide, and the precipitation that occurs between lead-2+ and the sulfide ion to produce lead-2 sulfide solid. Okay, in part B, we're asked which solid will precipitate first out of the solution, and we're given these two KSP values. So let's first do the precipitation calculation for the silver sulfide. Into the KSP expression, we know the concentration of the silver as 0.1 molar, given in the original problem. It would be 0.1 squared, given the KSP expression. And then we don't know the concentration of the sulfide, so I've just put X for that. And I set it equal to the KSP value of 6.0 times 10 to the minus 51. Solve for X, keeping in mind that X is the sulfide ion concentration. And I get 6.0 times 10 to the minus 49 molar. When the sulfide ion concentration is 6.0 times 10 to the 49 molar from the added potassium sulfide solution, then the solid silver sulfide will precipitate out. All right, let's repeat this now for the lead sulfide. We're given the KSP as 3 times 10 to the minus 28. And we know that the KSP expression for the lead sulfide is the lead concentration times the sulfide ion concentration. Remember, we're trying to find the sulfide ion concentration. So the lead concentration is given as 0.1 molar. We solve for the sulfide ion concentration and get 3 times 10 to the minus 27. So once we've added a concentration of sulfide ion equal to that 3 times 10 to the minus 27 from the added potassium sulfide solution, the lead sulfide will precipitate out. All right, so for the precipitation of silver sulfide, we found that the sulfide ion concentration needs to be 6.0 times 10 to the minus 49 molar, and that the lead sulfide, the sulfide ion concentration needs to be 3.0 times 10 to the minus 27 molar. So this is for the silver sulfide, and this is for the lead sulfide. So we can see here that the silver sulfide has less of a silver concentration need than the lead sulfide. And so what that means is that we'll reach that concentration first in our addition of potassium sulfide. And the silver sulfide will precipitate out first. And if you look at how much bigger the difference in concentration is here, what we're trying to get to happen is for all of the silver sulfide to precipitate first, leaving behind only lead sulfide in the solution.
To a solution containing 0.100 molar concentrations of silver and lead ions, a 0.200 molar potassium sulfide solution is slowly added. See how much of the first ion is present when the second ion begins to precipitate. Silver sulfide precipitates first, we've established that. Lead sulfide begins to precipitate when the concentration of the sulfur ion is 3.0 times 10 to the minus 27th. KSP of silver sulfide is 3.0 times 10 to the minus 28, and that will equal the concentration of the silver ion squared. And why is that? Well, we have a 2 over here in the formula. And then the sulfide ion. Plug in the numbers. We have 3.0 times 10 to the minus 28 equals the concentration of the silver ion squared times 3 times 10 to the minus 27th. We then get the concentration for the silver ion squared is 0.10. Take the square root of both sides, and our answer is 0.32.
A solution contains 2.0 times 10 to the minus 5 molar barium ions and 1.8 times 10 to the minus 4 molar lead 2 plus ions. If we add sodium chromate, which will precipitate first from the solution? Will barium chromate precipitate first with its KSP of 2.1 times 10 to the minus 10? or will lead 2 chromate precipitate first with its KSP of 2.8 times 10 to the minus 13? All right, so the first step is to determine which of the precipitation reactions is or are possible and write the net ionic equations. So we're going to write equations for both the barium ions and the lead ions precipitating with the chromate from the added sodium chromate. Okay, so here's the barium chromate, both the precipitation and dissociation, and the lead chromate, precipitation and dissociation reactions. We'll use these to determine which ion precipitates first. So I've carried over the dissociation equations from the previous slide so that we can write the KSP expression for the selective precipitate based on the KSP values provided. So for barium chromate, it's just the concentration of barium times the concentration of chromate equal to its given KSP value. And then the same is true for the lead chromate, lead 2 chromate. Lead concentration times chromate concentration is equal to the KSP that we're given. All right, so we're going to do steps 3 and 4 twice, starting with the barium. So step 3 is calculate the cation concentration. So the barium ion concentration is given as 2.0 times 10 to the minus 5. And then step 4 is to calculate the anion concentration. We can do that using the KSP expression to find that the chromate ion concentration is 1.05 times 10 to the minus 5 molar. All right, so let's repeat what we just did on the previous slide, but this time for the lead 2+ and the lead chromate rather than the barium. So we are given the lead 2+ concentration of 1.8 times 10 to the minus 4 molar. Okay. And given the KSP expression that we wrote a couple of slides back, we can calculate the chromate ion concentration. So it's just the value of the KSP given 2.8 times 10 to the minus 13 divided by 1.8 times 10 to the minus 4. And when we do that, we get 1.6 times 10 to the minus 9 molar. Okay, steps 5 and 6 in our process that we outlined earlier, we're not going to use because we don't need to calculate Q or compare it to KSP. And that's because we used our KSP to find what amount of our chromate would we need to add to get to that point where the precipitate will begin to happen. So we aren't comparing to say, did precipitation happen or did it not? We're saying, did we add enough of our ion for the precipitation to begin happening? And the reason that we did that is because we compared it, or we used our given KSP values to calculate it. And we know that KSP is equal to Q at equilibrium when the solution is fully saturated, and that adding any more than that, the ion will begin, or the compound will begin precipitating out. All right, so let's finally answer the question here. So in step 7, the cation that requires the smaller amount of the anion indicates which one will precipitate first, right? We're told if we add X amount of barium and X amount of lead, which precipitate will we see first, the barium chromate or the lead chromate? And so the answer is whichever of those two cations requires the least amount of anion to precipitate will precipitate first. So compare the chromate ion concentration needs for each of the ions. So for the lead ion, we got an amount that was 1.6 times 10 to the minus 9 molar. And for the barium ion, we got an amount that was 1.05 times 10 to the minus 5 molar. So which one requires the least amount of anion? The smaller number here is the 1.6 times 10 to the minus 9. So it is the lead ion that will begin to precipitate first. So we will see lead chromate precipitate first. Example 3, selective precipitation. Will a precipitate form if 50 milliliters of 0.200 molar barium chloride and 50 milliliters of 0.300 molar sodium sulfate, Na2SO4, are mixed together? The KSP of barium sulfate is 1.00 times 10 to the minus 10. All right, so step 1, let's determine which precipitation reactions are possible. So if we are mixing barium chloride and sodium sulfate, what can we produce? We can produce sodium chloride and barium sulfate. We know that this is always soluble with that group 1 metal. But we could form a solid with the barium sulfate. So our net ionic equation is the combination of those barium and sulfate ions to form a barium sulfate precipitate. And the dissociation equilibrium that exists is between this solid precipitate and the barium and sulfate ions. Once we know that, we can write the KSP expression. We're given the KSP as 1.00 times 10 to the minus 10. And KSP is the concentration of the barium ions multiplied by the concentration of the sulfate ions. All right, step 3, calculate the cation concentration. In this case, the cation is the barium ion. So we are given some information. What are we mixing? We're mixing 50 milliliters of 0.2 molar barium chloride. So that would be 0.2 molar barium. Okay. And 50 milliliters of 0.3 molar sodium sulfate. So in terms of our net ionic equation, 0.3 molar sulfate. So we are combining two solutions together. So we have an initial volume, 50 milliliters of 0.2 molar barium, but then we have the barium in 100 milliliters, So we need to find the concentration of the barium after the solutions are mixed together. So I can say M1V1 equals M2V2. So the concentration after mixing, once that equilibrium is established, right, we're saying that the moles before mixing of the barium is equal to the moles after mixing of the barium. So the concentration after mixing is the concentration before times the volume before over the volume after we combine. Okay. And we get a barium concentration of 0.100 molar. So by combining the two solutions together, we've decreased the concentration of the barium. That makes sense. So we're going to do the same thing for the sulfate. So initially we have 0.3 molar sulfate in 50 milliliters. And we combine it, it's eventually in 100 milliliters. So the concentration of the sulfate is 0.150 molar. Now that we have the concentrations of the barium and sulfate ions, we can substitute those values into the reaction quotient or Q expression. This is the same expression as KSP, but instead of using equilibrium concentrations, we're using those initial concentrations after the mixing. Okay, so the barium concentration is 0.10, the sulfate concentration is 0.15, so we get Q equal to 0.015. Compare Q to KSP to determine whether a precipitate will form. KSP is 1 times 10 to the minus 10. Q is 0.015. Since Q is greater than KSP, there will be a precipitate formed when you mix equal amounts of 0.2 molar barium chloride and 0.3 molar sodium sulfate. For the sake of completion, step 7 asks or tells us that the cation requiring the smaller amount of anion indicates which will precipitate first. This example didn't require us to do that because we only have the formation of one precipitate. To selectively precipitate metal ions from a solution that contains a number of metal ions, you should use the solubility rules and KSP values to determine an experimental strategy. The solubility rules may lead you to the identity of an anion that will result in separation of certain metal ions. However, at other times, the quantity of the added anion will be instrumental in the separation, given that the metal salts have different degrees of solubility, as seen in their KSP values.